What if I told you the most controversial part of a Tesla is not autopilot, not the screen, but the flow you never see? The structural battery pack is either the smartest move in EV manufacturing or a very expensive mistake. And today we are going to test that idea. Tesla did something wild. They decided the battery should not just be a box you bolt into a frame. Instead, the pack itself becomes part of the car's skeleton. Imagine your car's floor is no longer just holding the battery. The floor is the battery and it is also the structure that keeps the car stiff and safe. On paper, that sounds genius. In the real world, it changes everything for cost, crash repair, and even recycling. Let's start simple. A normal EV has a body and a battery. The battery pack is like a suitcase full of cells that you slide under the car and bolt in place. It is heavy, but if something terrible happens, in theory you can drop it out, fix or replace it, and keep the rest of the car. With Tesla's structural pack, the cells are bounded into a stiff slab of foam and metal. The slab is glued into the body between the giant front and rear castings. Together, they act like one big skateboard strong, light, very efficient to build. Why would Tesla do this? Three reasons: fewer parts, lighter structure, faster assembly. Instead of building a forest of little frame pieces and then hanging a pack under it, you cast the front, cast the rear, drop the pack in a like giant Lego tile, glue and bolt it, and you're done. Engineers love this because stiffness goes up, the body bends less, and the ride and crash performance can actually improve. Investors love it because every part you delete and every robot you remove from the line means more profit per car. So, where's the problem? The problem shows up when you stop thinking like a factory and start thinking like an owner, an insurance company, or a recycler. Imagine you get hit hard in an intersection. The crash bends the floor slightly and triggers the high voltage safety system. In a traditional pack design, a skilled shop might be able to drop the pack, inspect, swap modules, or at least replace the pack and keep the shell of the car. With a structural pack, the battery and the body are married. If the structure is bent in the wrong way, you might be looking at the total loss even if a lot of the car looks fine. From the outside, it can feel like this. One bad hit to the belly, and the entire car is now a giant battery waste problem. There is also the question of long term battery health. Every lithium ion pack will degrade with time, fast charging, and heat. With a non structural pack, you can at least imagine a future where someone offers third party pack swaps. New chemistry, new cells, same car. When the pack is structural, that kind of easy upgrades is far more complex. It is not like changing a laptop battery. It is like cutting out the spine of the car and grafting a new one. But here's the twist. From Tesla's point of view, this might still be the right trade. Why? Because most buyers keep cars for a certain number of years, not forever. If the pack and structure last 10 or 15 years with acceptable range, the fact that it is not easily swappable at year 20 may not matter for the first or even second owner. For the company, the big win is building millions of cars cheaper and faster now. For the environment and for policymakers, the question is different. Is this approach friendly to a future where we want to repair and reuse more and scrap less? There is also a BMS angle here, and this is where it gets interesting. When your battery is a structural part of the car, you really don't want it to fail early. A conservative and smart battery management system becomes even more important. It has to keep the pack in a safe temperature window, manage fast charging in a way that limits stress and catch early signs of cell trouble before they spread. This is not just about saving range, it is about protecting the backbone of the whole car. The more integrated the pack is, the less forgiving the design is to lazy BMS strategies. Think about it like this. With a modular pack, you can afford to be a bit more aggressive. Worst case, you pull a pack, refurbish it, and keep the car. With a structural pack, you're running a high-stake games. The BMS is the guardian keeping the structure healthy. If it misjudges aging or pushes fast charging too hard for too long, you're not just losing a battery, you're weakening a part of the chassis. That is why you see conservative charge curves and strong limits at high state of charge. People complain that charging slows down after 60 or 70%, on a structural pack that is not just about comfort, it is about survival. So, is this whole thing a revolution or a flop? The honest answer is that it is both at once, depending on where you stand. From a manufacturing and structural engineering point of view, it is brilliant. You get a stiffer platform, fewer parts, and faster line. From a service and repair point of view, it is scary. Small accidents can turn into large bills. Replacing the pack is closer to restructuring the car than swapping a component. From a sustainability point of view, it forces the industry to get serious about pack level diagnostics, gentle fast charging, and end of life dismantling, instead of pretending those problems can be solved later. The key moment is this: the structural packs lock in the idea that the battery is not just the accessory, it is the car that pushes everyone from designers to BMS engineers to treat the battery health as a first class design target, not just an afterthought behind range and 0 to 100 acceleration. If we get that right, structural packs could give us lighter, safer, cheaper EVs at scale. If we get it wrong, we end up with a new wave of disposable cars that are insanely hard to repair. If you want to understand the brain that keeps these packs alive and actually protect your own battery, then BMS course link is in the description. Thank you.